Imagine for a moment that you are holding a magnifying glass, peering ever closer at the very fabric of reality. As you zoom in beyond atoms, beyond the quarks inside protons, you eventually reach the very structure of space and time itself. What do you see? Is space-time smooth like a continuous fabric, or does it break apart into something more granular, more fundamental? This is the question that loop quantum gravity, LQG, attempts to answer. It is one of the leading contenders for a theory of quantum gravity, a theory that seeks to unite Einstein's general relativity with quantum mechanics. It suggests that space and time are not continuous but instead made up of tiny, discrete loops woven together into a vast cosmic web, an idea that could revolutionize our understanding of the universe. For over a century, physics has been built on two towering pillars. 1. General relativity, GR, Einstein's masterpiece, which describes gravity as the curvature of spacetime caused by mass and energy. It works beautifully on cosmic scales, explaining black holes, the expansion of the universe, and even GPS satellites orbiting Earth. 2. Quantum mechanics, QM, the strange and counterintuitive world of tiny particles, where things exist in superpositions, teleportation, quantum entanglement, is real, and particles can behave like waves. It governs everything from atoms to subatomic particles. Both theories are incredibly successful in their respective domains, but there's a huge problem. They contradict each other. Quantum mechanics assumes that space and time are a smooth, continuous background, while general relativity treats them as dynamic entities that can bend, stretch, and even disappear into singularities, like inside a black hole. This clash becomes especially obvious in extreme environments, such as inside black holes or during the first moments after the Big Bang. In these scenarios, gravity is so strong that quantum effects should come into play, yet general relativity breaks down completely. To resolve this paradox, we need a quantum theory of gravity. This is where loop quantum gravity enters the scene. Loop quantum gravity proposes that space is not a smooth continuum but instead composed of discrete, quantized loops of gravitational fields. These loops form an intricate, ever-changing network known as spin networks, evolving over time in a process called spin foam. Imagine zooming into the fabric of space. Instead of a continuous field, you see tiny, interconnected loops, somewhat like a woven mesh of microscopic threads. These loops are the fundamental building blocks of spacetime. They are indivisible, like the pixels of a digital screen, except that they define space itself rather than an image. This radical idea solves several deep problems. It eliminates singularities. In general relativity, black holes and the Big Bang lead to infinite densities, singularities. But in LQG, space cannot shrink indefinitely. Instead, it reaches a minimal size, preventing the formation of singularities. It suggests that time itself may be quantized. Just as energy comes in discrete packets, quanta, time might be broken into discrete units rather than flowing continuously. It provides a possible explanation for the Big Bang. Instead of a singularity, the universe might have emerged from a big bounce, where a previous universe collapsed and rebounded into ours. But how does LQG work? Let's break it down. 1. The fundamental units, spin networks. The mathematical foundation of LQG is based on spin networks, introduced by Roger Penrose in the 1970s and later expanded by Abhay Ashtekar, Lee Smolin, and Carlo Rovelli in the 1980s and 1990s. A spin network is a graph where edges represent quantum states of space, and nodes represent interactions between them. These networks evolve dynamically, shaping the geometry of space itself. To visualize this, think of a spider's web where each thread represents a quantum of space. The web isn't static, it constantly shifts and reconfigures itself based on quantum interactions. 2. Spin foam, the evolution of spacetime. When you introduce time into spin networks, they become spin foams. This is where things get even more fascinating. A spin foam is a dynamic structure representing how quantum space changes over time. You can think of it as a film strip of spin networks, where each frame represents a different quantum state of space. As the frames change, space itself undergoes quantum fluctuations, bubbling and shifting like a restless ocean. 3. The discretization of space. One of the most striking predictions of LQG is that space itself is quantized. This means there is a smallest possible unit of space, much like Planck's constant defines the smallest unit of action in quantum mechanics. The fundamental unit of length in LQG is the Planck length, approximately 10⁻⁻35 meters, far smaller than anything we can currently observe. Below this scale, space ceases to be space, as we know it. It becomes a quantum foam of fluctuating loops. If LQG is correct, it has mind-blowing consequences for our understanding of the cosmos. 1. No more singularities in black holes. General relativity predicts that inside a black hole, space and time collapse into a singularity where gravity becomes infinite. But in LQG, the loops of space prevent this from happening. Instead, black holes might lead to a new, expanding region, perhaps even a new universe. 2. The Big Bounce instead of the Big Bang. LQG suggests that the universe did not begin with an infinitely small singularity but instead contracted from a previous state before rebounding into the expanding cosmos we observe today. This could mean that our universe is part of an eternal cycle of expansions and contractions. 3. Time might not be continuous. If space is quantized, time might be as well. This would mean that instead of flowing smoothly, time jumps from one quantum moment to the next, like frames in a movie. This could revolutionize our understanding of causality and the nature of reality itself. 4. A step towards quantum gravity. Unlike string theory, which requires extra dimensions and unobservable entities like vibrating strings, LQG works purely within the four-dimensional spacetime we observe. It does not rely on speculative entities, making it a more grounded approach to quantum gravity. LQG is a beautiful and promising theory, but it is not yet complete. Some major challenges include lack of experimental evidence. Since the Planck scale is far beyond our current technology, testing LQG's predictions is incredibly difficult. The nature of time. If time is quantized, how does it interact with classical time as we experience it? Connection to the Standard Model. While LQG explains gravity, it must still be unified with other fundamental forces, like electromagnetism and the strong and weak nuclear forces. Loop quantum gravity is one of the most intriguing attempts to reconcile Einstein's general relativity with the strange world of quantum mechanics. By proposing that space itself is composed of tiny, discrete loops, LQG offers a radically new perspective on the nature of reality. If it proves correct, it will revolutionize our understanding of the cosmos, showing that the universe is not a smooth, continuous fabric but rather a shimmering web of quantum threads. Black holes may lead to new universes, time itself might be quantized, and the Big Bang could be just one phase in an eternal cosmic cycle. The quest for a true theory of quantum gravity is still ongoing, but one thing is certain: the universe is far more mysterious and fascinating than we ever imagined.